Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking a bit about work and energy in a uniform electric field. So this is sort of our introduction to this general topic. At this point we've covered forces, electrostatic forces, we've covered Coulomb's law, we've covered Gauss's law, we know what electric fields are, all that. What we don't know is about how much work they do. So let's begin with the basic definition for work. So work, which we usually use a W in these introductory classes for, work is usually defined by force dotted with displacement. I will use the letter S to represent displacement because this could be in 3 dimensions. So this could, for example, look like the X component of force times the displacement along X plus the Y component of force times the displacement along Y plus the Z component of force times the displacement along Z. Okay, so that is one way of finding work. The other, of course, would be to note that this is also equal to force times displacement, both magnitudes, times the cosine of whatever angle exists between your force vector, let's say that's this way, and your displacement vector, which may be this way. So if this is S and this is F, then this right here would be angle theta. So that is work, that is physics. This all is just physics 1 stuff. And it also is true, by the way, to add to this system over here that you could think of this entire statement as just being force parallel times displacement, or force times parallel component of displacement. Either of those is a valid way of looking at it. So now we come to the other part of this discussion, which is we want to do this for the case of a uniform electric field. Okay, so uniform electric field basically means your electric field is pointing more or less in the same direction everywhere, with more or less the same distance between one field line and the next. That is what it means to be a uniform electric field. Okay, so now let's imagine that I take a charged particle. This particle has charge Q, and I move it some distance along this axis. It may or may not be the electric field axis. So this distance right here, for example, might be my distance S. How much work have I done to this particle? Well, we know from physics from the last chapter that force is equal to Q times E, where this E represents the electric field, Q represents the charge. So similarly, force would represent Q times vector E. Vector E is uniform everywhere, and therefore the work being done on this system would look like Q times E dotted with S. And so that ends up being Q times E times S times cosine of the angle. Technically speaking, this right here is my angle, but I'm actually going to get the same result if I just use this angle in here. So cosine of angle theta. So that is how much work is being done in a uniform electric field. So if I'm simply moving along electric field lines then the electric field will do some work on my particle based on how far I move, based on how strong the field is, and based on how much charge I have. So that is fairly straightforward, I hope. The other part of this is potential energy. So it's worth recalling what the definition for potential energy is. So here is potential energy. I like to use the letter U for potential energy. Some authors and textbooks use a capital P with a subscript of E for energy, or maybe they just write PE. And then the other one that some have used is E sub P. For obvious reasons, I don't want to use E sub P because we're using capital E for the electric field. So I'm just going to use a U here. So what is it that potential energy is telling us? Well, you could think of potential energy as the potential for some, let's call it conservative force or conserving force within a system to do work on an object in the system. So this is a functional definition for potential energy. So what does that mean about this potential energy? Well, it means that if you allow a force within the system to do work on an object, then you are reducing how much potential energy is left in the system. How much potential does that have to do further work? So, for example, if I have a rock and I've got the ground down here, the amount of work that could be done on this rock by gravity is equal to whatever the mass of the rock is times whatever the gravitational field strength is, so basically m times g, my force, times however high above the ground the rock is. So we might say something like U equals mgh in this case. And that means that as the rock falls, so maybe the rock moves from here to here, so this would be like a delta H. Then the change in potential energy is going to be related to the change in the height of the rock. So delta U, oops, this is a U, is equal to m times g times delta H, except for that as this rock is falling down, my potential energy is also going down within this system. The work that has been done by the by gravity in this case is taken away from the potential energy being stored by the gravity and the rock. So in this case, delta H is basically negative. Work done is positive. Delta U is negative. And so the important point in all this is that sign of work done by force in the system is opposite of the sign of the change in potential energy. And so that basically tells us that any time that we allow a force in a system to do work on the system, we're kind of taking potential energy out of the system. And any time that we move an object in such a way that we have to work against a force in the system, a conserving force in the system, then we're basically storing more potential energy within the system. So, reminder, what makes a force a conservative force? Well, if I take an arbitrary path for an object, so it starts and ends at the same location, if the same total amount of work is done regardless of the path that I take to get from start to finish, then this force is going to be conservative. So notice that I've drawn 3 different paths. If total work done for all 3 paths and any other possible path, so if total work done is same for all paths, and specifically, and it is 0, then the force is conservative. So if I start and end in the same place, and I have the same 0 net work done, then it's a conservative force. If I start and end in the same place and I don't have the same amount of work being done, it's a non-conservative force. So an example of a conservative force, let's write some examples here. Conservative forces might include gravity, springs, like from Hooke's law, the Coulombic force, so electrostatic force. Those all are conservative. Non-conservative might include drag, friction. If you count pushing an object with your hand, so pushing with hand, etc. Those are not conservative forces. So that actually is a decent description of work done in and by a uniform field. It's worth maybe doing a single quick example to close. All right, our example is, suppose that we have a particle of known mass and charge. It's placed into a uniform electric field, and then it's allowed to move along the field lines for 2.7 meters. If it was initially at rest, we want to know how much work is done on it and what its final speed is. So the solution to this is as follows. The work done is equal to the charge times the electric field times the distance traveled, so QES, times the cosine of the angle between E and the displacement. That is 0 degrees, so cosine of 0 is 1. This means that I have 31 millicoulombs, that's 3.1 times 10 to the minus 2 coulombs, times 4.8 kilonewtons per coulomb, so that is 4.8 times 10 to the 3 newtons per coulomb, times the distance, which is 2.7 meters, times cosine of 0 degrees. Plug all that into your calculator to get an answer. This gives a total work done of 401.76 joules. With 2 significant figures, we would maybe call that 4.0 times 10 to the 2 joules. So that's how much work has been done. We can then use the kinetic energy, K, is 1/2 mv squared, which means that V is equal to 2K over m square rooted. So that gives us after some unit conversions, a total speed of about 364 meters per second.